Last episode, we built the derivative from the ground up, the limit of a difference quotient, 2 examples by hand, Newton and Leibniz, Cauchy in the 1820s. Today, we cash in. Computing a derivative from the definition is the right thing to do once or twice for understanding, and the wrong thing to do for the rest of your calculus life. 3 rules handle every polynomial, every linear combination of powers, and a huge chunk of what shows up in physics, engineering, and economics. The power rule, the sum rule, and the constant multiple rule. Each is a theorem with a short, satisfying proof from the definition. By the end of this episode, you'll differentiate something like 3x to the 5th minus 7x squared plus 4x minus 1 in your head, in about as long as it takes to read the polynomial. First, motivation. From the definition, getting f prime of a means computing one specific limit, f of a plus h minus f of a over h, as h tends to 0. We did it for x squared and for square root of x, both were fine. Now imagine doing it for x to the 7th. You'd expand a plus h to the 7th by hand, 8 terms from the binomial theorem. Now imagine a real polynomial, 5x to the 4th minus 3x cubed plus 2x minus 9. That's 4 separate limit calculations and then a theorem to glue them together. The pattern is screaming for a shortcut. We'll prove 3 theorems today, carefully, from the definition. After that, you won't compute another polynomial derivative from scratch for the rest of the course. You'll just read the rules off the function. Here it is. For any positive integer n, the derivative of x to the n is n times x to the n minus 1. In words, bring the exponent down to the front as a multiplier, then subtract 1 from the exponent. That's the entire rule. 3 quick sanity checks before we prove it. Take n equal to 1. The rule says the derivative of x is 1 times x to the 0, which is 1. And of course the line y equals x has slope 1 everywhere, so that's right. Take n equal to 2. The rule says the derivative of x squared is 2x, which we proved by hand last episode. Take n equal to 3. The rule says the derivative of x cubed is 3x squared, a brand new result. We'll come back to that one with a picture later, and you can sanity check the tangent slope visually. The rule is doing what it should. The proof is one careful expansion. We need the binomial theorem for x plus h to the n with n a positive integer. The theorem says you get a sum of n plus 1 terms. The first term is x to the n, with no h's at all. The second is n times x to the n minus 1 times exactly one factor of h. Then a term with h squared, weighted by n choose 2. Then h cubed, and so on, out to a final term that's pure h to the n. Notice which terms have which powers of h. Exactly 1 has no h. Exactly 1 has h to the first power. Every other term has h squared or higher. That structure is the entire proof. Let me bundle the higher order terms as h squared times some polynomial in x and h. We don't need to know what that polynomial is, only that it stays finite as h goes to 0. Now run the definition. The derivative of x to the n is the limit, as h tends to 0, of x plus h to the n minus x to the n all over h. Substitute the binomial expansion into the numerator. The very first term of the expansion is x to the n, and there's a minus x to the n sitting right next to it in the difference quotient. Those two cancel exactly. That cancellation is what makes the whole rule work. Without it, we'd have a finite number on top divided by 0 on the bottom, and the limit would blow up. After the cancellation, the numerator is n times x to the n minus 1, times h plus h squared times the polynomial q from the previous slide. Every term in the numerator has at least one factor of h. The denominator is also h, factor n h out of the numerator and cancel one factor with the denominator. We are working at h not equal to 0, so that cancellation is completely legal. Same logic as the x squared example last time. What's left in the difference quotient is n times x to the n minus 1 plus h times that polynomial q. Now take the limit. The first term doesn't depend on h at all, so it just sits there at n times x to the n minus 1. The second term is h times something bounded, and h goes to 0, so that term vanishes. What survives is n times x to the n minus 1. That's the rule. Box it. The rule we just proved only covers positive integer exponents. The good news is that the same rule works for every real exponent. The derivative of x to the negative 1 is minus x to the minus 2. The derivative of x to the 1/2, the square root, is 1/2 times x to the minus 1/2. The derivative of x to the pi is pi times x to the pi minus 1. Same pattern. Bring the exponent down, subtract 1. The proof we just did doesn't cover any of these cases, because the binomial theorem we used only works for positive integer powers. Modern calculus proves the extensions by other means. Negative integer exponents fall out of the quotient rule next episode. Rational exponents come from implicit differentiation in episode 9. All real exponents come from logarithmic differentiation in episode 8, where we rewrite x to the alpha as e to the alpha times the natural log of x and use the chain rule. For now, trust me, the power rule holds for every real exponent, and we'll use it freely. One free corollary even before the sum and constant multiple rules. The derivative of a constant is 0. The proof is one line. Plug f equal to c into the definition. The difference quotient is c minus c over h, which is 0 over h, which is 0 for every non-zero h, and the limit of 0 is 0. Done. The picture explains it without any algebra. The graph of a constant function is a horizontal line. At every point on a horizontal line, the tangent line is the line itself, slope 0. A constant function isn't changing, so its instantaneous rate of change is 0, full stop. You can also read this as the power rule applied at x to the 0, since any constant c equals c times x to the 0. The power rule predicts 0 times c times x to the minus 1, which is 0. Same answer two ways. We'll combine the constant rule with the constant multiple rule shortly, and together they make working with polynomials almost effortless. On to the sum rule, which says exactly what you'd hope. The derivative of f plus g is f prime plus g prime. The proof is almost suspicious in how short it is. Write the difference quotient for f plus g. The numerator is f plus g at x plus h minus f plus g at x. Regroup as f at x plus h minus f at x plus g at x plus h minus g at x. Divide by h, split the fraction, and you have the difference quotient for f plus the difference quotient for g. Each piece has a limit as h tends to 0 by assumption. The limit law for sums says the limit of a sum is the sum of the limits. So the combined limit is f prime of x plus g prime of x. Identical proof handles the difference, because subtraction is addition of a negative, and the sum rule extends to any finite sum by induction. The third rule, also one line. The derivative of c times f is c times f prime. Pull the constant outside the derivative. Proof, write the difference quotient for cf. Factor the c out of the numerator. The c sits outside the fraction now, and inside is just the difference quotient for f. The limit law for constant multiples says a constant slides outside a limit. What's left inside is the definition of f prime of x. Multiply c times f prime of x. Done. The geometric picture, multiplying f by c, stretches its graph vertically by a factor of c. Tangent lines stretch the same way. Every slope gets multiplied by c. If f has slope 5 at some point, then 2f has slope 10 there. The rule is the algebraic version of that picture. Now we package the four results. Power rule, sum rule, constant multiple rule, constant rule, into a single algorithm for polynomials. Given any polynomial, walk term by term. For each term, apply the power rule and the constant multiple rule to pull the coefficient through and differentiate the power. Then the sum rule glues all the pieces back together. The constant term, the one with no x in it, vanishes by the constant rule. The recipe for each term, bring the exponent down, subtract 1 from the exponent, leave the coefficient where it is, except now multiplied by the old exponent. The constant on the end of the polynomial dies. That's a complete algorithm for differentiating any polynomial. From a string of proofs straight out of the definition, we've manufactured a shortcut you can apply in your head. Let's use it. First worked example, the kind of thing you'll do thousands of times in calculus and physics. Differentiate 3x to the 5th minus 7x squared plus 4x minus 1. Walk the polynomial. For the first term, 3x to the 5th, the constant multiple rule says the 3 sits outside and we differentiate x to the 5th, which is 5x to the 4th. Multiplied by 3, that's 15x to the 4th. For the second term, minus 7x squared, the constant multiple is minus 7, the derivative of x squared is 2x, and the product is minus 14x. For the third term, 4x. The derivative of x is 1, that's the power rule with n equal to 1, so the derivative of 4x is just 4. For the last term, the constant minus 1, the constant rule gives 0. Add everything up. The derivative is 15x to the 4th minus 14x plus 4. Quick sanity check. At x equal to 1, f prime of 1 is 15 minus 14 plus 4, which is 5. So the tangent line to the original curve at x equal to 1 has slope 5. The original function value at x equal to 1 is 3 minus 7 plus 4 minus 1, which is minus 1. So the tangent at the point 1, minus 1 on the curve has slope 5. The whole calculation took about as long as it took me to read it. Second example, designed to flex the fractional and negative exponents. Differentiate square root of x plus 1 over x. The move is to rewrite everything as a pure power of x before you start differentiating. Square root of x is x to the 1/2. 1 over x is x to the minus 1. So f is x to the 1/2 plus x to the minus 1. Now the power rule does both pieces. For x to the 1/2, the rule says 1/2 times x to the 1/2 minus 1, which is 1/2 times x to the minus 1/2. For x to the minus 1, the rule says minus 1 times x to the minus 1 minus 1, which is minus x to the minus 2. By the sum rule, glue them with a plus, taking care that the second term carries its minus sign. The derivative is 1/2 x to the minus 1/2 minus x to the minus 2. If you want the answer back in the language of the original problem, 1 over 2 times the square root of x minus 1 over x squared. Compare that to last episode, where we spent an entire slide rationalizing the numerator to compute the derivative of square root of x from the definition. The shortcut got us the same answer in 2 lines. That's the whole point of the rules. Third example, and the most interesting one, differentiate the quantity 2x plus 1 squared. There are 2 ways to do this, and I want you to see both, because they preview an idea we'll formalize in episode 6. Method 1, expand first. 2x plus 1 squared is 4x squared plus 4x plus 1. Now apply the rules. Derivative of 4x squared is 8x. Derivative of 4x is 4. Derivative of the constant one is 0. Total, 8x plus 4. Method 2 is the chain rule preview. Don't expand. Treat the inside, 2x plus 1, as a single quantity u. The outside is u squared. Differentiate the outside first as if u were a single variable. The derivative of u squared is 2u, which is 2 times the quantity 2x plus 1. Then multiply by the derivative of the inside u, which is the derivative of 2x plus 1, which is 2. 2 times 2 times 2x plus 1 is 4 times 2x plus 1, which is 8x plus 4. Same answer. The point of method 2 is that for more complicated insides, say sine of 3x squared plus 5, you absolutely cannot expand first. The chain rule is what lets you peel off the outer function from the inner without doing any algebra. 2 episodes from now, we'll prove it from the definition. For today, file it away. Let me hammer the power rule home with a picture for the n equal to 3 case. The curve y equals x cubed climbs slowly through the origin, passes through 1, 1, and shoots upward to the right. By the power rule, its derivative is 3x squared. At x equal to 1, that derivative equals 3. So the tangent line at the point 1, 1 has slope 3. Write the line. Point slope form, y minus 1 equals 3 times the quantity x minus 1. Simplify, y equals 3x minus 2. Now look at the picture. The red dashed line is y equals 3x minus 2. The blue curve is y equals x cubed. They kiss at the point 1, 1 and pull away from each other as you move further along. The tangent is the unique straight line that hugs the curve at that one point. If you zoomed in tight around 1, 1, you couldn't tell the curve from the line. That is what a derivative is geometrically. The number 3 is the answer to how steep is x cubed at x equal to 1? And the power rule produces that number with 2 operations: bring down the exponent, subtract 1. Before we close, a warning that single-handedly accounts for a huge fraction of wrong answers on first-year calculus exams. The sum rule does not have a product analog. The derivative of f times g is not f prime times g prime. It looks like it should be by symmetry with the sum rule, but it is flatly wrong. The cleanest counterexample uses the power rule itself. Take f equal to x squared and g equal to x cubed. Their product is x to the 5th, and the power rule says the derivative of x to the 5th is 5x to the 4th. Now do it the wrong way. F prime is 2x, g prime is 3x squared, and the product of those is 6x cubed. 5x to the 4th and 6x cubed are not the same function. Plug in x equal to 2. 5x to the 4th at 2 is 5 times 16, which is 80. 6x cubed at 2 is 6 times 8, which is 48. Different numbers. The product rule fixes this. It says the derivative of f times g is f prime times g plus f times g prime, a mix of original functions and their derivatives, not just the derivatives. That's next episode. Same warning for quotients. The derivative of f over g is not f prime over g prime. The quotient rule patches that one too. For now, just remember the negative result. When functions multiply, their derivatives do not. A short historical note before the recap. Isaac Newton, during the plague years at Woolsthorpe in 1665, extended the binomial theorem from positive integer exponents to all real exponents, what we now call Newton's binomial series. Where the classical binomial theorem gave a finite sum for x plus h to the n, Newton's extended version gave an infinite series for 1 plus x to the alpha, with alpha a fraction, a negative number, or an irrational. Term-by-term differentiation of that series, which Newton did freely without anyone able to justify the move, gave him the power rule for all real exponents. He had the answer in the late 1660s, he just couldn't defend it. Leibniz, working independently, knew the integer exponent case in the form d of x to the n equals n times x to the n minus 1 times dx. The general real case has to wait for the 19th century, when a clean theory of logarithms and a proven chain rule combined to give the slick proof we'll see in episode 8. The rule is older than rigorous calculus. Why does this video matter for what's coming? 3 reasons. First, every polynomial in the rest of calculus is now differentiable on site, and there is no calculus problem in this course that doesn't, at some point, ask you to differentiate one. Second, every rational power, square roots, cube roots, 1 over x squared, all the way out to x to the pi, falls under the same rule the moment you rewrite it as a power of x. Third, the sum and constant multiple rules generalize beyond polynomials to any linear combination of differentiable functions. As we add sine, cosine, the exponential, and the logarithm over the next 4 episodes, these rules will be waiting for them. The bigger techniques still to come. The product rule, the quotient rule, the chain rule. Don't replace these 3, they combine with them. By the end of next episode, you'll handle things like x squared times sine of x, where the product rule and the power rule live in the same line of work. Where we landed today. 3 rules and 1 bonus corollary. The power rule, derivative of x to any real exponent, is the exponent times x to 1 less than the exponent. We proved it from the definition for positive integer exponents using the binomial expansion, and deferred the general case to episodes 5, 8, and 9. The sum rule, derivative of a sum, is the sum of the derivatives by the limit law for sums. The constant multiple rule, a constant slides outside the derivative by the limit law for constant multiples. The constant rule, free from the constant multiple rule, the derivative of a constant is 0. 3 worked examples. A pure polynomial, square root of x plus 1 over x, and 2x plus 1 quantity squared done 2 ways. 1 pitfall to file away, the derivative of a product is not the product of the derivatives. That gets fixed next episode by the product rule. Newton glimpsed the general power rule in 1665 with his binomial series at Woolsthorpe. Leibniz knew the integer case independently. 19th century analysts pinned down the general real exponent case using logarithms. Next time, the product rule and the quotient rule, the 2 rules that handle multiplication and division of functions. See you there. The power rule turns a long limit calculation into a single line of arithmetic. The way this channel turns into something useful is 1 like, 1 comment, 1 share at a time. Thanks for adding to the total. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.